localized states. Start like Pascal and Altshuler did with non-interacting fermions. Okay, I'm going to assume we have strong localization, so we have strong enough disorder, so all single particle eigenstates are localized. We might be in 1, 2, 3 dimensions. And so the Hamiltonian, and I'll put a knot on it, because we're going to add interactions, looks in terms of the creation and annihilation operators for a fermion in the eigenstates of the single particle Hamiltonian. It's just this simple Hamiltonian here. We have the eigenenergies. We have a sum over all single particle eigenstates. We have the eigenenergy and the number. Right? So it's a very simple Hamiltonian. Just a bunch of two-state systems. Right? Each eigenstate, each single particle eigenstate is a two-state system. It can either be empty or occupied. Right? So it's a two-state system with random splittings. And so we might as well also think at the same time about a spin model. So here's an equivalent spin model. Two states. I've got the same splittings. The factor of 2 there because the sigma has +1 and -1, whereas this has +1 and -1 as its eigenvalues. This one has 0 and 1. Okay, so these at this stage these are really the same system. Although of course, once things start moving around, they're different because these guys have fermion commutation relations and spins don't. As long as it's not at this stage, they're the same problem. Okay. And so then, and this is familiar, but let's view this as a many-body problem. So these are many-body Hamiltonians. And we can look at the eigenstates and the spectrum and the dynamics of these systems. And they are, in some respects, the same as what we're calling the many-body localized phase. The real many-body localized phase with interactions has some subtle differences which aren't yet here in these non-interacting problems. But these things, which are simple, actually contain a lot of the physics of the many-body localized phase. So since they're simple, let's discuss them a little bit first, because it's a reference point that we can then work away from. Okay. So there are 2 to the n eigenstates, all localized. Right? And what do they look like? In the spin language, they just look like the eigenstate, the basis states I was talking about before. They're simultaneous eigenstates of all the sigma z's. Right? And then the energy is the sum of these energies with either plus ones or minus ones, depending upon whether the spin is up or down. Or here, you add up the energies of the occupied orbitals, right, to get the energy. Right? So the eigenstates just they might look like this: up 1 across, up 2 across, down 3 across, blah 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 across, up. That equals 1 to n. I'm doing finite systems. Okay, so these eigenstates are all localized. Okay. They do not obey TH. I look at a subsystem in this eigenstate, it doesn't look at all like equilibrium, right? If I'm in this eigenstate and I look at spin 3, it's down. Even though the energy might be really high. Or even though that may be totally incompatible with what it would do thermodynamically. denoted by ETH. And if we look at the dynamics, actually, let me just say things.
Sorry, why do you say it doesn't obey ETH? That's just like, that's the full state of the whole system. But I thought
This is the state of the whole system. So this is an eigenstate of the whole system.
Right, so, but why do you say
Right?
it's not?
And it's at a certain energy.
Right.
Right? And let's just pick one at random. So say we picked an eigenstate at random.
Right.
So it'll be a high entropy state. It'll correspond to infinite temperature. And so if I looked at a subsystem of a system that's in infinite temperature, its probability will be the identity operator. It'll be equally likely to be up and down. Right? Whereas this guy, none of these spins look like they're at infinite temperature. They all look like they're at zero temperature. Okay. So it's totally athermal. Some of them look like some of them are in their local ground state, and some of them are in their local excited state. Right? So it's
But I think the way you define ETH is you look at subsystem and see if, once you look at the reduced density matrix, starting with that, say, pure state, density matrix for the whole system corresponds to a pure state, and then look at the reduced density matrix, ask whether that state is a thermal state.
yeah. That's what I was trying to say, right? So here's the eigenstate.
Right.
The reduced density matrix of spin 3 is actually a pure state corresponding to spin down,
Okay.
right? And so that's either, that looks like zero temperature. It's either zero temperature approach from positive or zero temperature approach from negative, whether we're in the excited state or ground state. It doesn't look at all like the temperature that this state would correspond to, unless this happens to be the ground state or the highest excited state of the system, right? In every other, right. So two of these eigenstates obey the ETH, namely the ground state and the highest excited state, right? Because there, all the spins agree on what the temperature is. It's zero, and they agree on its sign as well, whether it's 0 plus epsilon or 0 minus epsilon, right? But every other eigenstate doesn't satisfy the ETH. Okay, they have Poisson energy level statistics. There's no level repulsion between these eigenstates. There's no matrix elements between them. Two eigenstates that are almost degenerate, it's just because when you added up these numbers, they happen to add up to almost exactly the same number. Right? But you could get that with a two completely different eigenstates could happen to add up, but just by chance, to the same energy. Right? And there wouldn't be any level repulsion between those two. Okay, so they Poisson level statistics, unlike in the thermal regime where you have random matrix level statistics. They have no entanglement, which is a special case of area law. It's also a special case of volume law. But in this case, this no entanglement is a special case of area law, where the area law term happens to be 0. And in fact, if you go back, so this is no entanglement in the basis, right here I'm writing it in the basis of the single particle eigenstates, right? And there's no entanglement, right? If I went back, stepped back a step further and went back to the original type binding model and asked about the entanglement, then if I made a cut, I would actually cut some of these states which have some weight on one side of the cut and the other side of the cut. I would actually get some entanglement. I would get an area law entanglement due to the eigenstates that were occupied, and I happened to cut them through when I cut the system. I would get area law entanglement.
So would you have ETH for?
No. ETH you get volume law entanglement. Okay. Right, so we're at non-zero. So I'm assuming we're picking a state that corresponds thermodynamically to non-zero temperature. So a finite fraction of the spins are flipped away from either the ground state or the excited state. So there's no entanglement, right? And this is actually really area law. And these are all These are all properties of the many-body localized phase, which survive interaction. Actually, all the things I'm going to list right now. Okay, so now let's actually ask, what if we're not in, these are statements we can make about the eigenstates. Yeah?
Yeah, I'm sorry. If you have finite localization length, then don't you have finite entanglement? Doesn't that mean, again, like an area law entanglement?
Okay, so entanglement is a property of how you cut.
Yeah.
Okay? If you cut, so every eigenstate is on one side or the other of the cut, which is what I'm, right, in this picture here, right, I would cut maybe between, so some of these are on one side of the cut and some of these are on the other side of the cut, right? And each one of these represents a single particle localized state. So if I cut in this picture here, I'm not cutting any localized states in half, right? They're all purely on one side or purely on the other. Then I get no entanglement, right? Now if I go back to the tight binding model, where the eigenstates aren't strictly on the site, they actually have some support away from the site, then when I cut, I'm going to cut some of them, and I will get area law entanglement. And that's the generic thing, area law entanglement. Once you, even this model, even these models here, once I add interactions, I'm going to get area law entanglement in the many-body localized phase.
Okay.
Yeah.
So are you just saying here that non-interacting particles do not thermalize?
Yeah. Yeah. Now, what I'm telling you now is simple. But, yeah, it's simple. But a lot of the properties, or all the properties I'm going to emphasize right now, survive turning on the interactions in a whole phase. So they're actually properties which are not special to the non-interacting problem. Right? There will be some changes due to the interactions, but I'm not going to mention those until a bit later. Okay? So let's now think about some dynamics. Okay? So let's say we don't start in an eigenstate. Like, for example, we could start with a simple state to think about is, instead of putting the spins either up or down, let's put them pointing some random direction on the block sphere. Each one, we put it on some random direction on the block sphere. And then just make a product state out of that. So that's a non-entangled initial state. So what's going to happen? Under this Hamiltonian here, each spin is just going to alarm or precess at frequency epsilon about its z-axis. Right? So the dynamics in the spin representation is just spin precession. Independent spin precession. Very simple. So that's the dynamics. Right? And so there's no transport. No transport of energy, particles, information. Now again, in this model, or in this model, if I view these as the sites, there's no transport. But again, if I go back to the tight binding model, I have transport. The particles can move of order the localization length. So no transport means no transport over large distances. In reality, there's short distance transport. Not in this model, but in the tight binding model I started with. Leo?
Suppose if you have a translation invariant system, so then you're...
It's not translationally invariant. The system, right. I assume strong localization. I have strong disorder. All single particle states are localized. Sorry, finish your question.
Well, I guess I was going to ask is if alphas were K's, labeling momentum state, single particle state, then in the K bases it looks like...
That's right. If you cut in momentum space, you get this same structure, yeah. But that's not robust against weak interactions.
Okay.
Because physical weak interactions are not local in momentum states. In fact, they scatter things to all momentum, right?
Okay, that makes
sense. So that's right. This same structure, yeah, you're right. This could have been K. This could have been K squared over 2m, right? And I could say all these things. But if you actually think what they mean, right, no transport, you're talking about no transport momentum state in that picture, right?
but
And as soon as you put scattering, you take big hops in momentum space.
I guess I was saying, making connection with what you said for localized single particle states. There, you know, when you work with actual eigenstates, single particle eigenstates, then there's absolutely no transport.
That's right.
There's no entanglement at all. When you go to the original coordinate basis, you still have some transport over the localization.
Right, right.
On the other hand, if you had momentum eigenstates where you didn't have any transport, you go to the coordinate basis.
You go to real space, you get transport over the whole
Transport,
system.
right.
Yeah, exactly. Ballistic transport.
But you're saying the resolution is when you add interactions, then they're local and.
Yeah, so this structure is stable to adding weak, short-range,
Well, the other one.
in real space interactions. And physics seems to have the property that the interactions, you know, things tend to be local in real space. And locality in momentum space doesn't seem to show up very often. Okay, so no transport, what else does it say? There's no, the system, yeah, the system is not a reservoir which is thermalizing or doing anything to its subsystems. And there's no transport of information, which means the information about any initial condition I give it stays where it started. It doesn't go anywhere else. Right? And those are properties of this very simple system, but those are important properties of the many-body localized phase that do survive adding interactions.
David?
Which is what I'm going to do right now. Yeah?
If you take a disordered metal, I mean a wire, for example, and you increase its length such that you cross over from a diffusive into a localized machine.
Yeah, in 1D.
What's the one?
Yeah.
Then you cross over from detonizing spectrum certificates to not quite Poisson. And the point is that localized wave functions, which are very far apart in space, but very close in energy.
You're talking about the single particle level statistics, right?
Yeah, single particle, single
Okay.
particle.
So these guys are going to show level repulsion.
Yeah.
That's what you're saying.
Well, I was just asking about your Poisson energy level statistics.
Poisson many-body
Yes, many bodies.
energy level statistics. So even if you have some level repulsion here, which you do,
Yes.
once you start adding up an extensive number of these guys,
Yeah.
the sums don't show any level.
So, I mean, but there is no kind of correlation effect that could show up if this total sum kind of resonates and
No.
you wouldn't get any application.
No. You know, of course, you know, if you only had 6 of them, there'd probably be some residual of you know, it's probably a 1/n effect, which will go away in the thermodynamic limit. You know, the idea is when you do level repulsion, as you well know, you take the thermodynamic limit, the spacing becomes small, but then you scale things and you look at S,
Yeah.
right? And on the scale of S,
Yeah.
it's not going to know anything about the level repulsion that happened here when you take it large. That make sense?
Yeah.
So when we are not in the localized regime, but we are in the extended regime,
Single particle extended.
single particle
Yeah.
extended. So then also the energies are going to have level repulsion. But
You're still going to have Poisson energy level statistics
for the many-body system.
for the many-body problem, but that won't be robust against adding. As soon as you add interactions to that system, it will thermalize.
I see.
And so you will have, I guess, probably all these, well, you won't have this property. You'll have this property, you'll have this property, you won't have this property. So you'll have some of these properties and not others. And as soon as you add the interactions, even these two, the ones that you do have, will go away immediately. Because it will go into a thermal phase and obey ETH and have random matrix level statistics. Okay, so now we're going to add to our Hamiltonian. So let's add short range interactions. short range in real space, of course. Which are either particle-particle interactions here or spin-spin interactions here. And in fact, Anderson did spins. Bosco, Lehner, Altshuler did particles. And what Bosco, Lehner, Altshuler did, and in some sense, yeah, basically Anderson did as well, is we're going to treat those interactions perturbatively about the picture we're talking about right now. Okay. So let me just write a couple of Hamiltonians. So for the particles, H equals H naught plus, and a general interaction looks like this: alpha, beta, gamma, delta. B alpha, beta, alpha, beta. And this guy is non-zero only when alpha, beta, gamma, delta, all these orbitals overlap. Because the interaction is short range, it's a C dagger, C dagger, CC. You got to have all four particles, all four operators, within the range of the interaction. And let's say it's a delta function interaction or something, just for simplicity. So these eigenfunctions associated with all these guys have to overlap in order for this to be non-zero. Right? So this is short range in real space. Each of these orbitals, they each have a center in real space. Right? Think of it as a lattice. And each lattice is the center of a localized single particle. Each lattice site is the center of a localized single particle state. So they're not necessarily a regular lattice, but it's a bunch of points. Okay, so that's for the particles, and then for the spins, just like I showed you before, we do H naught plus. Right, and typically for particle interactions, this is just what you put this in and you stop, and that's it. For the spins. You can put two spin interactions, so sum over. Stick with my Greek letters: alpha, beta, sigma, alpha, j, alpha, beta. This is a 3x3 matrix of possible interactions between the spins. Three-component spin. And then you might have, and we'll see this, you might have multi-spin interactions. We'll get to that in a bit. So we add the interactions amongst the degrees of freedom we started with, but we certainly do not add any interactions with any other degrees of freedom, any environmental or any bath or anything like that. So it's still an isolated system. We haven't changed the number of degrees of freedom. We just added interactions. So this is, again, short range in real space. These guys either limited range or falling off exponentially or with a big enough power law. Okay. And so one thing you can do, and this is BAA, and I think it's a insight, is view many-body eigenstates of H naught as sites in Fock space. So each of these states here is a site in Fock space. So what geometry does this Fock space have? I guess it's a symmetric geometry. It's not a symmetric surface, right? But it's every point is equivalent, so it has something in common with Alex's symmetric surfaces. It's a hypercube, right? We have n things which are either up or down, or occupied or empty. So we have a Fock space which is a cube, the corners of a cube, n-dimensional cube. So it's a n-dimensional cube, hypercube, and it's the corners of that hypercube. Okay? And each one of those corners represents one of these eigenenergies of this thing. So there's the energies, site energies at each of these points in Fock space are different, right? Because each one corresponds to a different sum over these epsilon alphas. Okay, so we have a random potential, or a pseudo-random potential, in Fock space, on this cube. And then what do these terms do? These terms are hopping. Right? So what happens here is this becomes the potential energy in Fock space, and the interaction becomes the hopping term. Right? And the spin-spin interaction becomes the hopping term, because this can flip spins. Except there's also a diagonal term here, which is sigma z times sigma z, which doesn't flip spins, right? And so there's also sort of, and there's Hartree terms up here which don't move particles, right? But most of these terms move particles. And 8 out of 9 of these terms flip spins. Okay? And now those are the hoppings, right? And so we're back to single particle localization, right? Okay? And so let's take 2 eigenstates of H0 that are nearby in Fock space, so that there is one of these terms hopping. See, these terms here, these are, this is a 4 local operator, this is a 2 local operator. At most this flips 4 of the spins. This guy only flips 2 of the spins at most. Right? And so the states which are connected by the hopping is short range in this space. Right? So a hypercube has a distance, right? And there's corners that are nearby and corners that are far apart. Right? And it's only short range hopping. Right? And so let's just think of 2 of these eigenstates. So these are now eigenstates of H0. And here's another one here, M, eigenstate of H0, right? And they're at, let's say E0 here is the eigenenergy for H0. And they have some splitting, which is just the energy of the spins that got flipped, going from here to here. And then there's a hopping term, which goes from one to the other, which is either J or V, right? And so the sort of very brief summary of BAA is if JV is much less than E sub n minus E sub m, you're going to be strongly localized in Fock space. Your eigenstates will be pretty similar to the nearby states due to this hopping. And that's the best perturbation theory they could use, and they couldn't find any flaws in that as to some non-perturbative or higher order effects which would destabilize it. And they concluded that the many-body localized phase with these properties survives to some non-zero value of these interactions. They were working at low temperatures, but it's not really important to the argument as far as I can tell. And Vadim Oganessian and I, we generalized this to doing it at infinite temperatures and did some numerics, and their argument works at high temperatures, and it also survives numerical tests. Yeah?
Yes, sorry. I have a historical comment that what the framework which you just told us was actually done almost 10 years before Pascal, Wiener, and Schuler.
Yeah.
By and Schuler.
By Altshuler.
Yes.
Okay. Well, that's fine.
No, the main person who deserves credit for this framework is Levita.
Levita.
Right. So there was a paper by Schuler, Levita, and I know it because I was also on the paper. No, but really most of the credit should go to Levita. So this idea was entirely done in the framework of quantum dot, where there is no spatial structure. there is a Fock space structure.
Yeah.
And this
So the paper you're mentioning was just for quantum dots.
It's for quantum
Yeah,
dots, right?
yeah,
So it's
yeah,
not-
yeah. Certainly before BAA, there was an extensive development of this whole story for quantum dots. So I'm focusing on once it went to an extensive real space.
So far, there is no real space, right? So-
Yeah, there is. Yeah.
And you can repeat all these words about.
Short range in real space. Short range in this is all structure in real space.
If this space would be completely spatially extended, you can repeat precisely everything up to this point with no change whatsoever.
Oh, that's not true. If you actually look which matrix elements on the hypercube are present or not, it's very different. There's many fewer present in this problem than on the quantum dot. Because you only have matrix elements, see, on the quantum dot, you've got these for every alpha beta, you have a matrix element, right? So this is much more sparse in terms of the hopping.
In the initial basis, right? But
Yeah.
but the fact
Yeah.
that the many body Fock space is still partitioned into very localized pieces is still true.
Yes, yes.
There exactly the transition happens, it indeed depends very much.
Right.
But philosophically it's all there. You don't
Yeah. Although here, as you approach the phase transition, you have a localization length in real space which diverges. And I don't think you have that in the quantum dot, anything analogous.
You have a phase transition as function of energy.
But you have a,
Between
do you have a localization?
localized eigenstates and extended eigenstates.
Right, but there's no structure analogous to the real space structure that occurs here.
There's no real space structure.
Yeah,
But
right.
in energy space,
Yeah,
the many body states
right.
undergo phase transition.
Yeah,
That's a question.
yeah. I guess, yeah, I'm probably showing my prejudices that when I thought this was something happening just in Fock space, I felt I really didn't, it was, my focus on this tends to be in real space. It's something happening in real space, and that's really important. And there's also something happening in Fock space. That's sort of the viewpoint I take, that there's also something happening in Fock space, but what's really important is happening in real space. So that's my viewpoint, and that's why I present it this way. But that's sort of a prejudice. Because once I realized, I should focus on real space, I learned a lot more about the problem than I had before. Right? Found all sorts of stuff. Yeah.
So the argument that for J and P much smaller than En minus En, keep the states still localized. Should I see this as in the context of Anderson localization in an infinite dimensional space?
Of a very special problem of Anderson localization in an infinite dimension, a very special infinite dimensional space, right? Of course, it's infinite dimensional as n goes to infinity,
Right.
but it's very small in the
Right.
sense that it's only two sites in each direction, right? So it's a funny kind of d goes to infinity limit, right? The dimension is getting large, but the space is small in Fock space,
I
right?
suppose that these were like bosons or something, so you actually have a much larger Fock space. In that case,
What do you mean?
mean that you could have two particles at the site, three particles at the site, and so on.
Oh, okay. Yeah, that's right. Yeah, you can have in each site more than two states. Yeah, yeah. And then you'd have a cube with more than two sites. Yeah.
Right. So, it being infinite dimensional, would we expect that the threshold for when it becomes delocalized becomes smaller as you increase the dimension? In other words, we take this space. Let's say these are bosons, which can have any amount of any occupation number, and then we take n going to infinity. So we are now looking at a hopping problem, random site potential hopping problem
Of
But-
bosons.
of bosons as d
Yeah.
tends to infinity. I mean, it
No,
could
it's
be
not d
bosons.
tends to infinity. It's
Well, d is equal to capital N, right? The number of
that's the
sites.
dimension in Fock space.
Right.
Yeah.
So I
N
think-
is equal to L to the D, where this is real space, this is the
Right.
size in real space.
Right. So, but this problem, that the lower part of the blackboard, is actually a hopping problem in Fox.
In Fox space, yes.
Right. So, as we increase the number of sites in the system, then we
By
by
changing the number of states of the spin, or by increasing n?
n by
Increasing n, okay.
because the number of sites in the system is infinite, because it's a bosonic Fox space.
Okay.
So then we are actually looking at the problem of whether you have a localized phase in an infinite dimensional system.
Yeah, but it has, the thing is, the direction of increasing the boson number on one site, that direction which corresponds to one direction on this cube,
Yes.
there's a force pushing that back to 0,
Mm-hmm.
right? So you don't really, although that goes off to infinity, it's uphill, right? And if you're at a given energy, you only go a little ways up, and so it's not an infinite space in that direction, right? It's formally infinite, but it's not accessible at that without going to infinite energy.
What's the force? Right there?
It's
Or the
here.
energy of
So
it?
say these are bosons,
Oh, I see.
right? This is these, now if these are bosons, these guys have to be positive, they can't be negative, right? And going to large N corresponds to going to high energy, right? And so it would be a space in which there's, first of all, there still is a corner, which is no bosons,
Right.
and there's strong forces linearly pushing everything down into that corner.
So finite T.
Yeah.
So
And if you're at a given energy, you're not exploring that space. So there's no way you would delocalize in that space out to that infinity, because it's a totally different energy.
So the size of the system will be given by the temperature.
Yeah, or the energy. Yeah, the energy. I don't like to say temperature because there isn't a temperature.
There isn't a
The energy.
temperature, nothing's going back.
Okay, so I've just given an informal argument for why the localization that's here can survive adding interactions between the particles or interactions between the spins. As long as the splittings of the eigenstates of H naught are bigger than the hopping terms, it should stay localized. Right? And that seems to be true. Okay. Right, and as I said, Bosco, Lehner, Altschuler made this argument for non-interacting problem actually at low temperatures, but the argument is fine for going to high temperatures, even infinite temperature, and it's fine for spins as well. And it's Anderson more or less knew, although they didn't really say explicitly in his paper. Okay, and so the picture I'm telling you is that the eigenstates of in the many-body localized phase, the eigenstates of the many-body problem are like these guys, but dressed with short-range quantum fluctuations due to these hops. And that's, as far as we can tell, an accurate picture of what's going on in the many-body localized phase. And I'll put a little more substance on that picture later today or tomorrow. Tomorrow morning, right? Should I announce that? Have you, the schedule for tomorrow, this revision, is this official?
Yes, it's official.
So we have an official revision of tomorrow's schedule, which is Altland, what? Altland, Hughes, Altland? That's the sequence of lectures tomorrow. And Kamenev will finish on Friday with a double bill, right? Hmm? Oh yeah, Stamper Kern's also talking about Friday. Yeah. So there's... okay, so where am I? Right. Okay, so at weak interactions, it stays localized. You turn the interactions up, or you turn down the disorder to make these smaller. And eventually you hit a phase transition. And the phase transition is from the many-body localized phase with these properties to the thermal phase where the ETH applies and that I was talking about earlier in previous lectures. So there is a phase transition there. In any dimension, yeah. It's a quantum phase transition. So we asked, so in the naive early days of this, we were thinking, quantum phase transitions, you can always sort of do a mapping to a path integral, and there's a classical version of every quantum phase transition, and so we actually took classical problems where these are classical spins, with this Hamiltonian giving spin precession dynamics, and we look for many-body localization in a classical spin chain. But then after the summary of the story is, as far as we can tell, and there's another enormous paper by Bosco about this, is that you do not have many-body localization in classical systems, classical systems with nonlinearities, which are chaotic, or generic classical systems don't have many-body localization. They always thermal. It seems like they always thermalize. That's a challenge. Can you make an interacting classical system that's generic, so with nonlinearities, short-range interactions? Can you make a many-body localized phase there? It appears no is the answer, although that's not with. So this is the many-body localization phase transition is a quantum phase transition, but unlike standard quantum phase transitions, it's not happening at zero temperature. It's not happening in the ground state. It's happening in highly excited states. It's not a thermodynamic phase transition. It's only an eigenstate phase transition. So it's and it is poorly understood. There's no mean field theory. There's no scaling theory. There's no renormalization group theory. And there's no finite size scaling theory. So Arijit, Paul, and I set out to study it with finite size studies, to study a phase transition. But we, unlike usual numerical studies of phase transitions where you're guided by finite size scaling theory, you usually used to have a rough idea of what the finite size scaling theory should be when you do such studies. Here we didn't really know at all. So it was rather an adventure. Next is sort of summarize a particular model that we studied. And there was an earlier study with Vadim Oganessian and me doing a little bit of this, and I'll mention that, with a different model. I want to have some space. Actually, I'll just do it over here. There's enough room. Okay, so the model we use, so this is, I'll use 2010. So we use the spin chain, sum over I equals 1 to L, finite length, of course. So we took the Heisenberg spin chain. That's the other thing about studying many-body localization. There's no strong experiments on it. That's one of the big challenges with many-body localization is, what's the experimental system where one can really investigate this well? And so it's not clear what models you should be looking at. What are the models that are easiest to study this in? And so we there's a lot of people looking at a lot of different models, and it's not clear what is sort of the Ising model of many-body localization.
I'm going to give a question. So it seems like you have a bunch of different features in many-body localization, and similarly, it seems like these various features can all go together or go separately. Is there any reason to believe there's only two phases in total?
Yeah, just lack of evidence for other phases.
Okay.
Yeah, and also lack of a compelling scenario for another phase.
But I thought there are other phases based on what the recent paper about the.
No, that's all within the localized phase.
Right, but, okay, but that's.
No, he's talking about something that,
Well, there's two different localized.
yeah, no, there's lots of different many-body localized phases, but they're all many-body local, they all have the properties here I'm talking about. I'm just talking about what, as far as we know, are generic properties of the many-body localized phase. You know, they might have other properties like some symmetry breaking or topological order, or, you know, various spectral properties and things like this. But they have all these properties as well, right? Yeah, and a number of people are suggesting there's possibly some intermediate phases, but there hasn't been anything, you know, any proposals that have been fleshed out enough to, you know, even think about them seriously and decide, do you believe it or not, right? You know, it's more just like, oh, my numerics looks like there could be an intermediate phase, you know, but there's no description of, you know, and nothing really in the numeric, you know, of course, the numerics is not, you know, things are smooth in finite size systems, right? And so you can always say, oh, maybe there's an intermediate phase there, right? But, you know, there's nothing that really has features which says, oh, here's an intermediate phase and here's what it looks like it does, right? And so that's sort of the situation, right? This stuff is, you know, hard stuff to do anything very solid on, right? Now, actually, single particle localization, the existence of the localized phase is proven by mathematicians. But the many-body localized phase, not yet. That might happen. So I believe it's reasonable to expect that the existence of the many-body localized phase as a phase, there might be a mathematical proof in the near future, because I don't think it's a big step from single particle localization, because it is strong localization. But, you know, intermediate phases, and the thermal phase is totally out of reach to mathematics, right? And any intermediate phase, I'm sure, would be too. So we just, you know, we need to keep working on it, and, you know, if there's some good ideas of something else.
But I guess part of my question is also, like, can I draw sort of, you know, implication areas between, you know, certain properties up there? I mean, are some of them sort of logically, you know, required by others? Of those properties, but they also, could any of them in principle hold without the others holding?
Yeah.
Okay.
Yeah, no, I think that would be a nice thing, would be to try to think through which of these, you know, assume one is present and the other is absent. Can I show that that's just silly? Or can I make a system where that actually could happen? Right. Yeah, but I think, you know, this is all reasonably new stuff, and so I think there's a lot of opportunity for that, looking at it deeper. Yeah.
Just could you please comment on the condition J or V much smaller than the energy gap, especially considering that we just said that those energies have a Poisson statistics, so there are arbitrarily many close by energy levels.
But not that are connected by these matrix elements. Right, so the ones which are nearby differ in an extensive number of spins. Right, so these matrix elements, it just flips 4 spins. Right, and so you're just adding, so the energy difference here is just the sum of 4 of these numbers. So it's only 4. Right, and so you're not going to have, you know, you're not going to have really close ones. So of course, occasionally you'll have one, and you'll have. But that's the case in Anderson localization. There's always states which are nearby, you know, things which are hybridized strongly, even deep in the localized phase, just because they happen to be degenerate, right? In order to delocalize, you don't just need some of these to become strongly hybridized. You need a whole chain of them, which allows you to go ergodic or to go an infinite distance in the space. Right? But each one of these steps, yeah, you're only flipping at most 4 of these bits. And so it's not, you don't have a lot of freedom there to find something highly degenerate, very close to degenerate. Well, let me just finish writing this Hamiltonian. Okay, so we put a random field along the z direction So total sigma z is conserved as well as energy. So we have two conserved quantities, total sigma z and energy. And we pick these guys from a distribution which is a square distribution. So this is P of h from minus h to h. So these are independent, uniformly distributed random numbers between these two values. So that's the system we looked at. Periodic boundary conditions, so L plus 1 is equal to 1 on this index I. So we have periodic boundary conditions. And then we just did exact diagonalization, L up to 16. Multiple samples at each L in order to get statistical error bars. So you have to do multiple samples at each L. And then we looked at all eigenstates, which in some sense is infinite temperature. So if you had a Boltzmann distribution at infinite temperature, all states would be equally likely. All, I should put quotes on all. We looked at, you take all the states and you take the ones in the middle, right? The ones in the extreme, the ground state's going to behave very differently from the highly excited states. So we took the middle, sometimes the middle third, sometimes the middle half of the state. So all the states of high entropy. Leo?
Well, what's your density matrix of the whole system? Is it one state, is it a single state?
What is that? Here? Here?
Yeah. You know how?
Well, here okay, so far I'm only talking about eigenstates. So I'm talking about pure states. So I haven't yet talked about dynamics of this. I'm just right now talking about the eigenstates,
No,
which are pure states.
I'm trying to connect to what you talked about yesterday, where you talked about different possible density matrices for the whole system. That you could have the single
Oh,
state.
okay. No. When I say t equals infinity here, I don't mean I'm making a density matrix or an ensemble at this temperature. All I mean is when I do my statistical averages over the properties of the eigenstates, I give them all equal weight, which is kind of like being an infinite temperature. But it doesn't mean I have a bath or an ensemble or something.
But you take initial density matrix.
No dynamics. So what do you mean by initial? So right now I'm just talking about a Hamiltonian and its eigenstates and its spectrum. No dynamics yet, although of course the dynamics just follows from it. Right now, let's just stick with that, right? And then we can start talking about what the dynamics that's implied by that is. But there's a lot to say. Actually, I think I'm going to talk about the dynamics almost right away. Okay. So this thing has, so this has one parameter. The model has one, the size of the system, of course, but we're doing finite L, but we're trying to study L goes to infinity, right? So we have a system, it has, we believe, a phase transition in the limit L goes to infinity, and we've got one parameter, which is h, which is the width of the disorder. Okay? So we have a phase diagram, which is one parameter phase diagram, which looks like this, h. There's a special point here at 0, which was solved 2 years ago. The first real non-trivial many-body problem in quantum mechanics that was solved was this spin chain by beta. That's where the beta ansatz was involved. Okay, so that's 0 here. Okay. So that's an integrable system. But you add disorder to it, it crosses over to a phase that satisfies ETH. This crossover here is an interesting topic of research to a lot of people, but I'm not going to talk about it today. So that's the crossover from integrability to non-integrability. There's a phase transition, as far as we can tell, at HC of about 3.5. And I'll put error bars maybe of 1.0 on that, so big error bars. And over here is the many-body localized phase. And the BAA work is starting here, right? Strong disorder, weak interactions, right? So we could, right, there's implicitly a J here, and they're working at J equals 0, which is the same as H equals infinity, right? So they're coming in from this direction and saying this phase is stable over here. And what I want to do first here is just list a number of differences between these two phases that are of interest, and maybe make some comments about how we explored them. Right. So first over here, ETH is true, and over here, ETH is false. And we check this in ED. So I told you how you test ETH. Over here, when you compare two adjacent eigenstates and look at a subsystem, the difference is small, and it goes to 0 exponentially as you increase out, as expected. Over here, the difference is large. It's of order 1, and it doesn't change as you increase out. It seems to stay so that's something you see. So here there's, so in terms of the important thing in physics, over here we have spin, energy. So when I say spin, I mean as sigma z is a conserved quantity. So spin, energy, information are transported. So here we have transport. We have a non-zero spin conductivity, thermal conductivity. The information about the initial condition spreads that through the whole system, becomes volume law entangled. Whereas here, we believe in the limit of L goes to infinity, the DC transport is equal to 0. This we don't really check numerically. And that's strictly 0. Strictly 0 in the thermodynamic limit, even though you're in non-zero temperature. Yeah?
So this comparison of adjacent eigenstates is not sufficient, right, to prove this normalization? Is it
No, it doesn't prove it, it just tests it.
it's kind of like
Yeah.
a necessary condition, not sufficient?
Yeah. Yeah. We did some other tests as well, which I'll just mention in a little bit. But you know, as I've emphasized numerous times, none of this stuff is very rigorous or even really that well demonstrated, right? It's a story, makes sense, it survives the tests that have been done that you can do so far that people have thought of. But compared to a lot of other physical theories or theories of statistical mechanics, the types of tests that you're able to do are rather weak, right? Because we're talking about small systems. You can't go to very big sizes. So I just want to make sure nothing's being oversold here. Okay, so over here you get volume law entanglement, so the eigenstates. Eigenstates have volume law entanglement. And over here you have area law entanglement of the eigenstates. And we looked at this a bit, and in fact when we started we were thinking, oh, let's do a finite size scaling study of the entanglement spectrum. Because there was this nice paper from Calabresi, and I forget who the collaborator was, about the finite size scaling of the entanglement spectrum near a conformal critical point. Really beautiful stuff. And I was thinking, oh, that's cool. We could maybe do that here. But the data was just so noisy that eventually we gave up. But I think we got reasonably good evidence for volume law over here and area law over here. But we were focused on trying to find the phase transition, and it didn't help at all.
What kinds of tests would you do for large system size or larger system size?
For which? For this?
Sure.
Well, actually, well, I don't know. This is actually something that maybe should be revisited by someone. Can one do, we tried, but we tried very early in the study before we knew much about the problem, and we didn't go back to it. And, I think it might be an interesting thing to develop the finite size scaling theory of the entanglement spectrum. The entanglement spectrum has an enormous amount of information in it, right? You've got every eigenstate, and every eigenstate individually has an entanglement spectrum. So you just do one sample and look at the entanglement spectrum here. It's just an amazing amount of data. It's not like doing ground states where you only have one eigenstate and one entanglement spectrum. Here, we have an entanglement spectrum for every eigenstate, and there's 2 to the n of them, right? And so it's an enormous amount of data. It's very noisy because of the randomness, but it seems like something that there might be an opportunity there to do something, particularly now that the problem is understood better. When we were trying to do it, we were very naive, whereas now I think the general understanding of this whole situation is a lot better, and so maybe somebody could make some progress with that. I don't know. The many-body level statistics. So many-body level stats. This has already been mentioned, but I'm just listing the differences. Here they're random matrix theory. These Hamiltonians, it's all GOE. We're choosing orthogonal type Hamiltonians. Here it's Poisson. And this has been tested. This is actually Vadim Oganessian and I earlier in our first numerical paper. We looked at the spectrum and saw this change over here and estimated the transition in that model. The finite size scaling of this isn't that great, so it didn't look like a good thing for trying to locate the transition. But you can see the 2 phases very cleanly at these size L's in level statistics, particularly if you use the trick we invented of unfolding the spectrum in a different way than is traditional, because the disorder adds a lot of noise and makes it hard to unfold the spectrum, and so we invented an interesting little trick that you can read about.
What do you mean by unfolding the spectrum?
No, that's what Alex was talking about.
Okay.
Yeah. Figuring out, when you do the level statistics, you've got this S, which is the level spacing compared to the average level spacing. The problem is the average level spacing here is very noisy and hard to determine. And so there's a way around that where you don't even have to know the average level spacing, and you can still do level statistics. Which is sort of obvious, but somehow it hadn't been found before.
Could you remind us, so when we talk about ETH holding or not holding, you're talking about eigenstates somewhere in the middle of the spectrum, not all of the eigenstates.
Yeah, I'm talking about the middle of the spectrum. Right. If you just pick up an eigenstate at random, it's going to be a high entropy. It's going to correspond to what thermodynamically would be a high entropy state, something that would be near infinite temperature, and they have this property. Yeah, you're right. In this phase here, states way out in the tail are localized. Right? So whenever you have extended states in an Anderson model, if you go way out in the tail of the distribution, Lifshitz tails, you got localized states out there. Right? So here, this is right. So this phase, all the eigenstates are localized. Here, some of the eigenstates are thermal. In fact, most of the eigenstates are thermal, but there are ones out in the tails of the energy distribution which are localized. Good point. Yeah.
So can't you see it if you look at the IPR as a function of energy or something?
Yeah, the IPR is tricky because it's not a good measure. IPR is inverse participation ratio. Because even when they're localized, they're not that well localized in Fock space. Because you take a large system, you have these, right, you have a given state, and then you have local quantum fluctuations occurring, but they're occurring everywhere, right? And so even when it's localized, it occupies an extensive entropy of points in Fock space. So the localization of Fock space is it's rather weak, right? If you ask, what's the IPR, you would think it's an extended state because it's on an exponentially large number of sites. It's just a much smaller exponential than the total Fock space, right? So they're not localized like localization in finite dimensions, where a localized wave function has support on a finite number of sites. These ones have, their support is on an infinite number of sites. So in a certain sense, you look at Fock space, you might think, oh, it's not localized if you're careless. Right? And so the IPR doesn't do very well in this situation. People use it, but I think it's not the right tool. Yeah?
Yeah, sorry. So I'm trying to draw a distinction between the many-body localized phase and the conventional Anderson insulator phase. So do they have different properties? Is there some...
Yes. Well, one property is only the eigenstates have area law entanglement. If you, in the many-body localized phase, and you start with a generic initial state and run to long time, it will have volume law entanglement. So there is information propagating in the many-body localized phase, spreading around. There's decoherence. So it's different. Right here, the dynamics is just spin precession. This statement becomes false, right? So this one, right, actually, I was careless here. So only the ones which are indented are stable to interactions. This guy, interactions, that's not the correct description of all the dynamics. Right? So there is a difference, and I'm going to get to that.
Okay, so but in a nutshell, you're saying that only the many-body eigenstates are localized. That there's something special about it. Did I hear that wrong?
No, the initial states, they stay, well, a generic initial state stays localized in a certain sense, but it's in a weaker sense than the non-interacting problem. Right? The non-interacting problem, there's no transport of anything, including information. There's no dephasing. Right? Whereas in the many-body localized space, there is dephasing. The system serves as a static spin bath, which gives each spin a finite T2, but still an infinite T1, if you know the nomenclature from dephasing.
I guess.
So whereas here you have an infinite T2 and an infinite T1, right? So there is a real distinction between many-body localized and non-interacting. But right now I'm emphasizing the things they have in common because this is simple, right? And so most of the properties of many-body localized phase are simple, but it does have some properties which are not so simple. Right? But I'm doing the simple stuff first.
So in some sense, this perturbation is relevant. That's what you want to say. So this V alpha,
right. There are some properties of the localized states which get changed significantly and qualitatively by turning on these interactions. Yes, and I'll get to that. Okay. And actually, let me. Right. So that reminds me. This statement. This is of energy and spin. There's no transport. But there is some quantum information which gets transported to large distances. But not all of it, just some of it.
So that's at the linear response level that you see is zero, you see small.
I think it's beyond linear response. That's actually another interesting question. I was thinking about that the other day, whether this is true beyond linear response, and I think it is true. I haven't really thought it through super carefully, but I think it may be true. That if you put a finite gradient in, it's localized. But that's a Yeah, this may be true even outside of linear response. I don't know that anybody's really said that in print, but I think it might be true. It's something, again, another thing to think about, seriously. Yeah? This part of my talk always gets an enormous amount of questions. That's why I love giving it. Yeah?
So, do ETH or many-body localization describe every possible thing that we have?
Well, that was a question before. Maybe yes, maybe no. At this point, okay, so if we let ETH include the integrable systems, at this point, in terms of serious discussions, where scenarios have been developed, the answer is yes. But it's not like we know that that's all the possibilities, right? Of course, there's the critical point, which is probably neither one nor the other, right? But in terms of robust things, right? Integrability is not robust. Integrability, as far as I know, I don't know that there's any integrable system that is robust against adding sort of arbitrary short-range interactions. So this isn't robust either. But this is a robust phase against perturbations, and this is a robust phase against perturbations. And those are the only two that we know about right now. But maybe there's more. That's like I say, none of this stuff is close to super solid arguments, so it's hard to make categorical statements. Okay, so this is decoherent, which is related to the information transport, right? You put some quantum information somewhere in here, it just spreads out over the whole system, and it's hard to retrieve. Whereas over here, you can make a permanent qubit. And I'll show you in principle how you do that. Although the recipe is one that maybe isn't at the point of being realistic yet. But you can do it in principle. So you can write a qubit on a many-body localized system locally, put some quantum information on it, and it'll be there forever. No loss. I'll talk about that. And then a little bit about dynamics, a little bit more about dynamics. Of course, this was about dynamics here. This is about dynamics, more about dynamics. Here you get diffusive transport, diffusion. So just a little bit over. When I say transport here, in this phase, the transport is diffusive. Right? And here there's no transport. But here we have entanglement. So this is something I was mentioning, and I'll elaborate. Entanglement, or equivalently quantum information, spreads with a distance r goes as log t. So highly subdiffusive transport of quantum information, or spread of entanglement distance goes as log time. And here, entanglement and information spreads. So this is now alluding to Kim's poster that you may have seen last night. He wasn't talking about a random system, but he was talking about a system that obeys ETH. The entanglement and the information spread ballistically, even though the conserved densities only move diffusively. So you have this difference here, slower motion of the conserved quantities than of the information. Same thing over here where they don't move at all, but the information moves logarithmically. Here the difference is bigger, t to the half versus t. Here it's only the difference between t to the 0 and log t. Although the difference between nothing and something, you could say that's big compared to the difference between something and something.
If the information spreads as log t, how can you have a stable qubit then? I mean,
Okay, this is from, I'll elaborate on that, okay? So the recipe, this is from a generic initial state, but there is a way to create an initial state where it doesn't happen. Right? Yeah, from a generic initial state, this is what happens, but you can make states where it doesn't happen. And I'll explain that in soon. And now this here, again, this is an eigenstate phase transition. It's not a thermodynamic phase transition. It's a phase transition in the dynamics. It has a lot of big changes, but it's not thermodynamics. And that's particularly vividly illustrated by saying, oh, let's look at t equals infinity. At t equals infinity, we know what the free energy is. Right? It's log 2 per spin, basically. And there's no singularity as you cross the phase transition. And that's not an illusion, as far as we know. Okay, so now I want to do, let me just say, okay, so in thinking about this, we could, so just maybe talk a little more generally, what kind of models can't have a many-body localized phase? So what is death to many-body localization? Of course, coupling to a thermal reservoir is. So you have to be isolated from the environment. But what kinds of physical systems at non-zero temperature automatically are reservoirs that will thermalize themselves, and they just can't have a many-body localized phase. And so the so it's talking more generally. So MBL is, let's say, unstable to Goldstone modes. So they have particularly, let's say, gapless. So if you have a continuous symmetry of some sort, you will have Goldstone modes, and Goldstone modes are non-localized in the limit. You take any Goldstone mode in any random system, which is a continuous symmetry, you go to low energies, the localization length goes to infinity, and those modes will be able to transport stuff and thermalize whatever you have. Right? So it certainly appears that systems with continuous symmetry, that's not, the Goldstone modes aren't gapped out by Anderson-Higgs mechanism or something, they're really there. You can't have them anybody localized phase. So that's at least something we're suggesting as a conjecture. And of course, two important types of Goldstone modes are, well, there's photons, there's phonons, and there's also spin waves, right? So a lot of natural physical systems, if you're coupled to those modes, and they really are symmetries and they're gapless, you're not going to have many-body localization. Of course, photons in a material with a random dielectric constant, you can localize them, right? So that's not a Goldstone mode.
What do you mean by Goldstone modes at the high energies where you're looking at here?
Well, you can be in a symmetry broken, well, first of all, you can have a continuous symmetry, right? You can be in a symmetry broken phase and be at non-zero temperature. Right? So I'm talking about a symmetry broken state at non-zero temperature. That's all. You don't have to be at infinite temperature, right? We looked at infinite temperature here because we were trying to do some numerics and we wanted to have one less parameter, so we set the temperature to infinity, so we had one less parameter. But the discussion is general. Right? If we turn on the temperature here, so let's put beta, the temperature along here, there's some phase boundary which presumably goes something like this, where as you go to lower temperature, either positive or negative, the many-body localized phase gets bigger thermal phase gets smaller. But this, trying to do this at a non-zero temperature, all of a sudden you have exponentially fewer states you're working with than you did at infinite temperature, and it's hard to get good statistics. And so you know, we could see this moving a little bit, but it's tough to work it. It's tough to do it away from infinite temperature. So an awful lot of the numerical work on many-body localization is done at infinite temperature for that reason, just to get enough statistics to do a decent job. You go through all the work of diagonalizing these big Hamiltonians. You got all these eigenstates. You know, use them. Don't just use a tiny set of them like you would if you weren't at infinite temperature. Okay, so that's one thing. Particles moving in the continuum in d greater than or equal to 3. We know that particles moving in the continuum in d greater than or equal to 3 at high enough energies, the single particle states are extended. That's pretty general. And those extended states, you will have some population. If you're at a non-zero temperature, you will have some population of those states, and they'll transport stuff, and they'll presumably thermalize your system. Although, maybe not. Maybe if they're way up at high energy and they have some exponentially small population, maybe you can survive it. But I think this is true. It's possible it's false, but I think it's true. That kills NPL.
What about the critical case of say, the wrong extended state in the middle of the Landau level? Is that death to NBL?
Yeah. It looks like quantum Hall systems, the extended states at the Landau level, in the middle of the Landau level, look like they would kill many-body localization. At least we've thought about that and couldn't come up with a scenario whereby many-body localization could survive those extended states in the middle of each Landau level. But that's an interesting question. Maybe we've got that one wrong.
But that for the short range interaction, you're thinking. What happened with the long range?
Yeah, well, that's the other thing, right? Okay, it's unstable to long range. Or to long range interactions or hopping. And exactly what the threshold is, we have ideas, we might have it wrong, and I don't want to go into the details of that, but there's some power law. The boundary between many-body localization being viable and not viable is some sort of power law in the interactions in the hopping. And the details of that, let's not go into it. So that's another. So these are sort of the three main, common physical things that look like they're going to mess up many-body localization. Yeah, and I guess quantum Hall, right? But generally, having extended single particle states is a problem, right? I assumed all the single particle states were localized right at the beginning. Yeah. Yeah.
So I was trying to understand why this curve. Why do you expect it to bend this way rather than?
Because the density of states goes down. So right, you have the highest density of states here at infinite temperature, and the density of states goes down. Right? That's almost the definition of infinite temperature.
Oh, this is temperature decreases.
Well, it's beta, inverse temperature. Okay. So this is negative temperature, and this is positive temperature. This is beta. And so the density of states going down makes it harder to find something to hop to, and so it's easier to get localized. That's sort of an informal argument. Okay, so let me just, so I'll do a little thing. Actually, I'll give a simple example here, and it'll be a homework problem. Okay? And then we'll continue tomorrow. So this transport of information is illustrated by this simple two-side Hamiltonian, H1, sigma Z1, plus H2 sigma Z2 plus J sigma Z1 sigma Z2. Okay? And these numbers, there's no, they're random numbers and nothing adds up and cancels. Okay, so you can diagonalize this. The eigenstates are the simultaneous eigenstates of sigma Z. They're all just product states, right? The eigenstates are up, 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 down, up, and down, down. They have no entanglement between the two spins. So they're like, let's say here. So no entanglement. And so you'd think, oh, maybe, the eigenstates have no entanglement, so this system, there's no entanglement, right? But if you start it in an arbitrary initial state, which is any linear combination of these, with weight on, I think at least, well, there's some, so you take a general initial condition with weight on all four, and look at the dynamics, it'll generate entanglement between the two spins. So go through that exercise. It's just a simple exercise in unitary time evolution. And in fact, one thing you might ask, which I haven't done, and I think it's an interesting question, yeah. So there's also initial states which don't generate entanglement, obviously the eigenstates and various linear combinations. So do I have to have weight on all four? I think maybe I only need weight on the three. I think if I have weight on three of them, I will generate entanglement. If I have weight on just this guy and this guy, I'll do that one too. So give an arbitrary linear combination of just this guy and this guy, so some sort of bell-like state. No, that's not allowed. Okay, so you want an initial state which has no entanglement. Right, yeah, that's the point, right. So we want to start with an initial state that, like these eigenstates, has no entanglement. So it's some psi 1, some state of the spin 1, pure state of spin 1, cross pure state of spin 2. And it's not an eigenstate. So it's going to have weight on all four, because neither this nor this is pointed along the z direction. It's pointed off somewhere away from the z-axis. Right? So it's going to have weight on all four. It has no entanglement. And then just look at the time evolution and show to yourself that it gets entangled. And that's how entanglement propagates in the many-body localized phase. The eigenstates have no entanglement, but dynamically entanglement propagates. I shouldn't say propagates. Right? I said I will never say entanglement propagates. Entanglement is not a conserved quantity. Entanglement spreads. It's like a rumor or a disease.
That's the logarithmic spreading you were talking about?
Yeah. So effectively what happens in the many-body localized phase is, in terms of the natural variables, which I'll talk about tomorrow, they interact. So there are some normal modes of the many-body localized phase, and they interact with interactions that fall off exponentially with the localization line. And that's how the entanglement propagates. But it only produces dephasing. It doesn't flip spins. It only scrambles the x and y components of the spins and not the z component. So that's sort of a summary of that. But I'll go through that in some detail tomorrow. Yep?
I have a question on the last part. If you have two different kinds of species of particles, but you don't have any gapless modes, do you think that mixing the two kinds of one particle will act as a bath for the other, and that will also lead to...
Well, I think you need both particles to be, you need both species to be localized. So you may have been looking at a paper by Grover and Fisher. No, okay. Look at the paper by Grover and Fisher, posted like a week or two ago.
So in what sense do you...
I don't believe the paper, but it speculates on this issue with an answer differently than the one I would give you.
In what sense is the information spreading? Because I mean, it seems like, if I put a spin echo on just my single site, I could get the information back, right? Especially at least in this model.
Well, you should figure out how to do that in the many-body localized phase.
The fidelity doesn't go to zero asymptotically even in the sort of single cycle cases, right? I mean, some of it just sticks around forever.
Yeah, if you know what your normal modes are in the localized phase, which you don't, and you can address it without addressing any of the other normal modes, then you can do a spin echo.
You do a perfect spin echo in that case, but I mean, it seems like you could get sort of...
Yeah, so the question is, if you do an imperfect spin echo, will you really have some of, it's possible that, but the information spreads, and then you do the entanglement spreads, and then you do the spin echo, and it comes back.
Okay, fine, so...
It's different from rumors in that respect. Yeah, so entanglement is different from rumors in that respect because, of course, you can have things which are entangled which become disentangled by some unitary time evolution. Now, diseases you could get healed, right? So it's more like a disease, a curable disease that spread. But the thing is, it's a just barely curable disease because it's only under very special circumstances that you can reverse entanglement, right? Generic circumstances, entanglement, you can't reverse it, right? So it's one of these diseases which pretty much is hopeless, but under very special circumstances you can cure it. Here you can cure it easily because it's only 2 degrees of freedom. But yeah, rumors you can never cure them. Actually, that's not true. You could just give them the truth, and they might believe you. If it's a false rumor. False rumors you might be able to cure. True rumors you can't cure. Okay, so any other questions? I think that's time to quit.
Yeah,